Welcome to Month 1 of the Senior DevOps Engineer track, Advanced Kubernetes and GitOps. This session is a step up from the DevOps Engineer track. The goal here is not to review what a pod is. The goal is to answer harder questions. How do you share a cluster safely between 40 teams? How do you build a platform that prevents humans from touching live state? And how do you extend Kubernetes with your own domain objects when the built-in primitives aren't enough? The 5 objectives on this slide are the exit criteria for today. By the end of this session, you should be able to design multi-tenant cluster boundaries, build a GitOps flow that passes a security audit, and write a controller that actually reconciles, not just applies YAML. 4 hours structured in 2 halves. Hour 1 covers concepts, multi-tenancy models, CRDs, and the controller pattern. Hours 2 and 3 move to a live-kind cluster where you build the app of apps, deploy a CRD controller, and deliberately break things. Hour 4 is demo, peer review, and retrospective. 2 key constraints run through the entire session. First, everything runs locally on kind, no cloud subscription required. Second, the GitOps constraint is absolute. If you find yourself reaching for kubectl apply on a managed resource, stop. Make the change in Git and watch it converge. That discipline is the whole point of this platform. There are 3 multi-tenancy models, and the choice matters more than most teams realize. Soft tenancy via namespaces is the default because it is cheap and operationally simple. You get RBAC, resource quotas, network policy, and pod security standards. That is enough for most enterprise internal platforms, but it is not a hard boundary. The kernel, the CNI layer, and the node are still shared across tenants. If one team saturates the API server with a misbehaving list watch, every other tenant feels it. Virtual cluster. The cluster gives each tenant a virtual control plane running as pods inside the host cluster. The key benefit is that tenants can run different Kubernetes versions. The cost is roughly 300 megabytes of RAM per virtual cluster and additional operational surface. It is not a magic isolation solution. A breakout at the CNI or node level still crosses tenant boundaries. A separate cluster per tenant is the only true compliance boundary. PCI DSS, HIPAA, and GDPR auditors often require this level of isolation. The operational cost is real. Separate upgrade cycles, separate monitoring stacks, and multi-cluster Argo CD hub-spoke configuration. The decision matrix on this slide makes the trade-offs explicit. Cost-sensitive environments with no compliance mandate. Namespaces. Teams that need different Kubernetes versions. vCluster or separate clusters. Hard compliance boundaries. Only a separate cluster fully satisfies an auditor's requirements. Resource quota and limit range are mandatory in any multi-tenant cluster, and they are consistently confused, so let's be precise about what each one does. Resource quota sets the aggregate ceiling for a namespace. The API server enforces it at admission. If creating a new pod would push total memory requests past the quota, the create is rejected with no exceptions. The example on the left's 4 CPU requests, 8 CPU limits, 8 GB and 16 GB of memory, 50 pods, and 10 persistent volume claims. Notice it sets both requests and limits, not just one. Quotas that only cap limits let teams set 0 requests, which gives the scheduler no information for placement and leads to nodes that are overcommitted and pods that get killed under load. Limit range sets per container defaults and minimum and maximum bounds. The critical interaction between the two: if you have a resource quota in place and a pod's containers have no resource requests, the admission controller rejects the pod because it cannot account for it against the quota. Limit range fixes this by injecting defaults automatically. You should always deploy both together. The key distinction to remember: resource quota is the namespace budget. Limit range is the per container guardrail. One container cannot claim the entire quota when limits are properly configured. Default deny network policy is the only safe starting posture for a multi-tenant cluster. The YAML on the left has an empty pod selector, which selects all pods in the namespace, and lists both ingress and egress in policy types with no rules. That means all traffic is blocked. You then layer explicit allows on top, DNS on port 53 UDP and TCCP to kubectl, traffic from the ingress controller namespace, Prometheus scrape access from the monitoring namespace, and any cross-namespace service calls your application needs. The most common failure mode when deploying default deny is forgetting to add the DNS allow rule first. Without DNS, everything breaks immediately, and the error messages point at application services rather than at the missing DNS policy. Always add the DNS exception before anything else. Pod security standards are Kubernetes replacement for pod security policy, which was deprecated in version 1.21 and removed in 1.25. 3 levels exist. Privileged is unrestricted, appropriate only for system-level workloads like CNI plugins and node agents. Baseline blocks the obvious dangerous configurations: host PAD, host IPC, host network, privileged containers, and dangerous Linux capabilities. Baseline is the correct default for tenant namespaces. Restricted is maximum hardening. Workloads must run as non-root, privilege escalation is blocked, seccomp is enforced, and all capabilities are dropped. Enforce a level by adding a label to the namespace. Pod security.kubernetes dio enforce set to the desired level. You can also audit or warn, which logs violations or surfaces warnings without blocking the pod. Starting with audit, measuring your actual blast radius, and then switching to enforce is the lower risk migration path. A custom resource source definition is how you extend the Kubernetes API with your own domain objects. The anatomy has 4 building blocks that matter in practice. The OpenAPI version 3 schema validates the shape of every custom resource at admission. Without it, any YAML is accepted and your controller receives malformed input. Always define at minimum the spec fields your controller reads, and use the preserve unknown fields false setting to reject extra fields. This prevents API surface creep over time. The status subresource is critical for correctness. By separating status from spec, you allow the controller to update status without triggering a spec reconcile loop. Without this separation, every status write triggers another reconcile, creating a tight loop. Always enable the status subresource. Printer columns determine what kubectl get shows for your resources. Without them, kubectl shows only name and age. With them, you can expose ready state, replica counts, image tags, and any other useful fields directly in the terminal output. A CRD without printer columns is a usability failure for the operators and the developers who have to work with it. The conversion webhook becomes necessary when you evolve the CRD schema from version 1 alpha 1 to version 1 beta 1. The webhook converts between versions at admission and retrieval. Retrofitting a conversion webhook after the fact is significantly more painful than planning for it from the start. The controller loop is simple in concept, but has specific correctness requirements that trip teams up in production. In the observe phase, the controller watches the Kubernetes API via an informer cache. When a catalog custom resource changes, or when a deployment owned by that resource changes, the object key is enqueued for reconciliation. The informer uses list watch, not polling, so it is efficient by design. One important property: the controller always works from the local cache, not live API state. The cache is eventually consistent with etcd. In the diff phase, The controller fetches the current state from the cluster and compares it to the desired state derived from the spec. It computes the delta, what must be created, updated, or deleted. In the act phase, the controller applies the delta using server-side apply or strategic merge patch. It sets an owner reference, so that when the catalog custom resource is deleted, Kubernetes garbage collects the own deployment automatically. The most important correctness property here is idempotency. The reconcile function will be called many times, on every watch event, on resync intervals, and on error requeue. If it is not idempotent, you have a production incident waiting. In the status phase, the controller writes observed state back via the status subresource, sets conditions for ready, progressing, and degraded states, and requeues with exponential backoff on error. The backoff matters. A fast retry loop on a failing reconcile can saturate the API server. The reconcile skeleton on this slide is production grade. Get the custom resource. Ignore not found errors from deletion. Build the desired deployment, set the controller reference, apply via patch, and update status. Every step is necessary. Knowing when not to write an operator is as important as knowing how to write one. Most teams over-operatorize. Write an operator when the domain object requires continuous reconciliation, not one-time setup, but ongoing lifecycle management. A database cluster that handles failover, backup, and version upgrades. A certificate resource that auto-renews before expiry. A Kafka topic that manages partition rebalancing. These scenarios are right for an operator because the reconciliation requirement is continuous and the consequences of drift are serious. Write an operator when multiple resources must be atomically created and kept in sync in a way that humans reliably get wrong. Creating a deployment plus a service plus a config map plus a horizontal pod autoscaler that all depend on each other and keeping them in sync when any one is accidentally modified is exactly the kind of ongoing coordination an operator handles well. Do not write an operator for one-time setup. A Helm chart with a post-install job handles database table creation on first deploy perfectly. An operator that runs a migration job on every reconcile is over-engineering. Operators have runtime cost. They are always watching, always queuing, always reconciling. A job costs nothing after it completes. Do not write an operator because you want a UI. Backstage is the answer to that problem. A controller is a reconciliation engine, not a presentation layer. One separate issue deserves emphasis. The finalizer is a foot gun that can permanently block object deletion. A finalizer that is never removed leaves the object stuck in terminating state forever. If the controller crashes, the object cannot be deleted without manual intervention to patch out the finalizer. Always have a clear path to remove finalizers, even when the controller is unavailable. The app of apps pattern solves the problem of managing many Argo CD applications declaratively. Without it, you create applications by hand through the Argo CD UI or CLI, and there is no audit trail or version control for that process. With app of apps, one root application points at a directory of child application manifests. When you add a file to that directory, Argo CD creates the child application automatically. The root application in the example points at apps, dev with automated sync, including prune and self-heal. This means the root application manages itself, and adding a new child application file to the apps dev directory triggers automatic creation with no human action beyond the git commit. The routing follows naturally. Apps dev contains team.catalog.yaml, team B billing, YAML, and other application manifests. Each of those files is an Argo CD application pointed at the actual application's manifest repository. The root application manages applications. The child applications manage Kubernetes resources. When you have many similar environments, production, staging, development, across many applications, the natural evolution is to replace app of apps with application set and a generator. Instead of one file per application, you write a template and a generator list. App of apps is the right starting point because it is simpler to reason about and debug. Application set is the right destination when the repetition becomes maintenance overhead. Sync waves solve the ordering problem within a single Argo CD sync operation. Resources with lower wave numbers are applied first, and Argo CD waits for all resources in a given wave to become healthy before advancing to the next. The ordering shown on this slide is canonical, wave -2 for namespaces, which must exist before anything can be deployed into them. Wave -1 for custom resource definitions, which must be installed before any custom resources can be created. Wave 0 for operators and controllers, and wave +1 for application workloads. The annotation that sets the wave is straightforward. Argect darkt argoproj io sync wave set to the desired number. Sync hooks are the other ordering mechanism, and they work at lifecycle boundaries rather than within the normal resource sync. Presync runs before resources are applied, the correct place for database schema migrations. The sync waits for the presync job to succeed before applying any manifests, so a failed migration blocks the sync immediately rather than letting partially migrated state reach the cluster. Post-sync runs after all resources reach healthy status, the right place for smoke tests and notifications. Sync fail runs only when the sync itself fails, making it useful for cleanup jobs and alerting. The key distinction between waves and hooks: waves order resources within the normal sync operation. Hooks are additional resources that run at lifecycle boundaries and are cleaned up after execution. One common production issue: presync jobs that run longer than the Argo CD operation timeout, which defaults to 300 seconds. For long-running migrations, set the operation timeout explicitly on the application spec using sync options. App project is Argo CD's RBAC and allow listing layer. Every application belongs to exactly one app project. The default project allows everything and should never be used in a production environment. 3 things define what an app project controls. First, source repos, which Git repositories are permitted as sources for applications in this project. Setting this to a wildcard means any repository in the world, including a public repository under an attacker's control, can trigger a deployment to your cluster. Always be explicit. List the specific repositories that are authorized. Second, destinations, which clusters and namespaces applications in this project can deploy to. Restrict tenants to their own namespace prefixes and block access to platform-owned namespaces. Third, cluster resource whitelist, which cluster-scoped resources applications can manage. Most tenants should have none. They should only manage namespace-scoped resources. The most dangerous misconfiguration in Argo CD is source repos set to wildcard. It looks harmless, but it eliminates your supply chain boundary. In a supply chain attack scenario, an attacker with push access to any permitted repository has a direct path to cluster state. The correct process when a team wants to deploy from a new repository: a pull request to the platform team's GitOps repository, adding the new repository to the relevant app project. This creates an audit trail and a review gate. Granting teams self-service edit access to app projects defeats the purpose of having them. The sync policy setting is one of the most operationally consequential decisions in Argo CD, and the correct answer is different per environment. For development, automated sync with prune and self-heal is the right choice. Prune means resources deleted from Git are deleted from the cluster. Self-heal means if someone manually modifies a resource in the cluster, Argo CD reverts it within seconds. This creates a fast feedback loop where the cost of mistakes is low and the environment stays aligned with Git automatically. For production, no automated block at all means manual sync only. A human reviews the diff and initiates the sync intentionally. The change is deliberate and audited. The rule about self-heal on production is absolute. Never enable it. Consider what happens during a production incident when you need to make a break glass change. Adding an environment variable, adjusting a replica count, modifying a resource limit to stabilize a degraded service. With self-heal enabled, Argo CD reverts that change within seconds. Your on-call engineer is now fighting the platform at the worst possible moment. This destroys trust in the GitOps platform faster than almost any other mistake. The correct break glass pattern is to either commit the emergency change to Git and sync from there, or temporarily suspend auto-sync on the specific application, make the break glass change, document it in the incident ticket, and then commit to Git and re-enable sync. Part 3 of the hands-on lab is where you build a real controller from scratch and deploy it through the same GitOps flow you just configured. 4 steps. First, scaffold with kubectl. Initialize the project with your domain and repository path. Create the catalog API type and controller scaffold. Then run make manifests generate to produce the OpenAPI schema and RBAC markers. And make install run to install the CRD into the kind cluster and start the controller locally. Second, implement the 4 key pieces. Add the image and replicas fields to the types file. Implement the reconcile method using the pattern from the controller slide. Add a finalizer for safe deletion. Then build the container image and push it to a registry the kind cluster can reach. Third, and this is the critical point, do not deploy the controller with kubectl apply. Create an Argo CD application in your GitOps repository that manages the controller deployment. The controller is managed by the same GitOps flow as everything else on the cluster. This is how you avoid a category of drift where the control plane itself is not under GitOps management. Fourth, create a sample catalog custom resource in the app's dev directory and watch the controller reconcile it into a deployment. A common mistake during this step is forgetting to add RBAC markers in the controller source code. The markers are Go comments prefixed with plus kubectl RBAC that kubectl reads to generate the cluster role. Without them, make manifests produces a controller with no permissions, and the reconciler logs forbidden errors on every attempt. Running through failure scenarios deliberately is how you build real confidence in the platform. If you can break it and recover it cleanly in a controlled environment, you know the recovery paths work under stress, not just on paper. Scenario 1. Stuck sync. Push a manifest that references a container image tag that does not exist in the registry. The deployment is created, but the pod fails to pull the image. Argo CD marks the application as degraded. Recovery uses the Argo CD CLI. Check the application's sync history, then roll back to the last known good revision. This is a Git-coordinated rollback. It sets the sync target to a previous commit revision without modifying the Git history. Scenario: drift. Use kubectl edit on a managed deployment to change the replica count directly in the cluster. Argo CD detects the drift within 3 minutes, which is the default resync interval. In a development environment with self-heal enabled, Argo CD reverts the change automatically. In production without self-heal, it shows out of sync and waits for a manual sync decision. Scenario 3. Finalizer hang. Delete a catalog custom resource while the controller is not running. The resource enters terminating state and stays there. The finalizer removal requires the controller to call the remove finalizer function and update the object. With the controller down, this never happens. Recovery requires directly patching the finalizer's array on the object to empty it. This bypasses the controller's cleanup logic, which means any deployments owned by the custom resource are now orphaned and must be cleaned up manually. Scenario 4. Quota breach. Change a catalog spec to request 50 replicas. The controller creates a deployment requesting 50 replicas. The resource quota blocks the pods from being scheduled. The controller's status shows 0 observed replicas and a not ready state. Resolution. Either raise the quota in Git and sync the change, or roll back the replica count in Git and let the autosync restore the working state. The challenge ties everything from this session into a realistic production scenario. You are a senior DevOps engineer at Bistec, a logistics SaaS company. 40 internal teams share a single Kubernetes cluster running 128 workloads. Everyone has cluster admin access through a shared kubeconfig. There is no GitOps. CI runners apply manifests directly. Drift between live state and Git is present in roughly 30% of workloads. 3 of the 4 incidents last quarter were caused directly by humans editing live cluster state. This is a real pattern in organizations that grow fast without governance. The current state is deliberately bad, because that is what you will be asked to fix in real engineering roles. The target state is achievable in today's session. Tenants isolated by namespace and app project. All workloads reconciled from Git via Argo CD. No human writes to the cluster except through a documented break glass procedure, and a self-service experience where opening a pull request causes a new application to appear in the development environment automatically. The scope for the challenge: 3 tenants, Team A, Team B, and Platform, across 3 environments, Dev, Stage, and Production, on a local kind cluster. The design must be transferable to a real production cluster without modification. 4 deliverables, 25 points each, totaling 100 points. Deliverable 1 is a multi-tenancy design document with an RBAC matrix. This is a design document, not a diagram. The RBAC matrix must show actual roles with actual permissions, not TBD placeholders. Resource quota entries must have numeric values. Network policy exceptions must be listed explicitly by port and namespace. The break glass procedure must be detailed enough that a stranger can follow it without prior knowledge. Deliverable 2 is a working Apps GitOps repository with the exact directory structure specified in the challenge brief. The key behaviors are: dev autosyncs with prune and self-heal. Production requires manual sync. Sync waves order resources correctly from namespaces through workloads, and both pre-sync and post-sync hook jobs are present and demonstrably execute during a sync operation. Deliverable 3 is a working catalog controller, not a kubebuilder scaffold with an empty reconcile method. The controller must create and update a deployment when a catalog custom resource changes, must remove the deployment when the custom resource is deleted using the finalizer, and must be deployed through the same Argo CD GitOps flow as every other workload, not via kubectl apply. Deliverable 4 is a postmortem for one real incident you triggered during the lab. A precise timeline, a mechanically correct root cause explanation, recovery steps that a teammate could reproduce exactly from the document alone, and evidence such as log excerpts or terminal output supporting each step. The non-functional requirements have specific numeric targets. Sync latency under 90 seconds for the development environment. The RBAC matrix readable in under 5 minutes by someone unfamiliar with the system, and controller reconcile latency at the 95th percentile under 2 seconds when running 100 custom resources. Today covered the foundational layer of platform engineering. You worked through how to design multi-tenant cluster boundaries that a security auditor can validate using namespaces, RBAC, resource quotas, network policy, and pod security standards in combination. You built a GitOps platform where Git is the only authorized path to cluster state, and you extended the Kubernetes API with your own domain objects using custom resource definitions and a controller that actively reconciles desired state. Month 2 shifts to the infrastructure layer, infrastructure as code at scale with Terraform and OpenTofu. The focus moves from cluster internals to the resources beneath the cluster, managing cloud infrastructure, designing reusable modules, managing state backends at scale, and applying the same GitOps discipline to infrastructure provisioning that you applied to workload deployment today. Before month 2, the offline milestones build directly on today's work. Replace the app of apps with an application set using a Git generator. Add a Kubernetes policy that rejects container images without a signature. Wire Argo CD notifications to a Slack or Discord channel for out-of-sync events on production. These are not optional enrichment activities. They are the patterns that distinguish a production-grade GitOps platform from a proof of concept.